we saw the definition of tail sigma algebra, we made some examples, and then we started, well, we stated and proved Kolmogorov-01 law, and then we started with results from real analysis about convergence of sequences that will be useful in the next session. However, what I would like to do is actually to start again from Kolmogorov-01 law. And hopefully I will explain it a bit better, it will be a bit smoother. And so, with that said, let's start. So, theorem, Kolmogorov-01 law. Which says that given a sequence G1 Gn of independent sub-sigma algebras of H, if we have this, then the probability of an event H is either 0 or 1 for any H in the tail sigma algebra. And the proof is the following. Consider G1, Gn, and Tn. This thing is an independency for any n. In the natural numbers. And so, since T is contained in Tn, we have that G1 ... Gn T script T is an independency, and we can rewrite this considering T, G1, G2, and so on, which is again an independency. Now call this thing T0 so that T0 is again an independency. It is simply a way to call this in a different way. And okay, so we are okay up to here. And all this relies on the fact that partitions of independencies are again independencies. Now consider H in T, consider H in T, script T, and G in T0. So, since, well, let's put it like this, since T is independent from T0, we have that the probability of the union of H and G factorizes into the product of the probabilities. And well, here I know that if we let H equal G, then we have the conclusion that we seek, even if I don't understand why we do it in this way. here it says but since t is contained in t0, well, in tn for any n, we have that t is contained in t0, and then for h equal g, we have that the probability of h is, well, of h union h, basically, well, oops, no, okay, the probability of h union g is the probability of the union of h with itself, which is the probability of h, and, well, it's the probability of h with itself, which implies that it can either be 0 or 1, because probabilities, like if you multiply two things, why? Because it's the same number. This is the same number, so if we have an example 0.1, 0.1, this would be different. So the only way for this to be equal if this is either 0 or 1, or 1, 0 or 1, 0 or 1, I think. So the probability of h is either 0 or 1, y punto. And from here, we started with the notions of convergence. Let xn be a real sequence where n is in the natural positive numbers, then we define the lim-inf over n of xn to be the supremum over m of the infimum, where m is larger than n, of xn, and the limit of the supremum over over n of xn is the infimum of the supremum. Of this sequence xn, n like natural number, and actually it's n greater than m, n greater than m. Okay, and we say that if the lim-inf of xn is equal to the lim-sup of xn, the limit of the sequence xn exists. After this, we introduced some notation. Oops. Notation. We call I epsilon of x the indicator on the interval epsilon plus infinity, which is 0 when x is smaller than epsilon, and is 1 when x is larger than epsilon. Correct? Yes. And here we have equality also. And then we have remarks. The first one being that a sequence xn of real numbers converges to a point x still in the real numbers if and only if this difference here goes to 0 as n goes to infinity. Secondly, a sequence xn of positive real numbers converges to 0 if and only if here we have the indicator maybe for any epsilon greater than 0 there exists some k greater than n, no, simply some k such that xn is less than epsilon for any n greater than k. And we saw a graphical interpretation of this. An alternative way of seeing this is that xn goes to 0 as n goes to infinity if and only if the sum of these indicators is finite for any epsilon greater than 0. Further, we have that the sum of these indicators plus infinity xn converges if and only if the lim sup of these indicators coincides with the lim inf of the same indicators and goes to 0. No, actually, forget about this. 0 if and only if the lim inf of xn is 0. And finally, we saw the Cauchy criterion. Cauchy. Given a sequence xn of real numbers this converges to x in R if and only if the limit as m and n go to infinity of this difference of the terms in the sequence is 0 for any m greater than n. Then we have a proposition. So if every subsequence that has a limit, let's write it in plain words. If every subsequence which has a limit, has the same limit, x, then what can we say? We say that the entire sequence, tends to the same limit. And moreover, if the sequence is bounded, and every converging subsequence has the same limit x, has the same limit x, then the sequence converges to x. Now we have a lemma about the behavior of lim_inf and lim_sup. Lemma: behavior of lim_inf and lim_sup. Which says the following: let xn be a sequence of real numbers which is positive, and xn be the average, which is the sum from 1 to n of xi over n. And let n be the following subsequence: nk, subsequence of the natural numbers with the limit over k of nk plus 1 over nk, which goes to 0. If I remember, no, which is a constant and is positive. Now, if xn bar, this sequence here, converges along n to x, then we have this relationship here, lim inf of x and bar bounded by the lim sup and is bounded above again by x times r, or r times x. And so this gives an idea about fluctuations of a sequence of averages in terms of the subsequence n and the limit x. I still don't understand well what this means, but in any case, it's okay. Now, let's take a look at Kelly's theorem. Kelly. Oops. Okay. So for every sequence Cn of distribution functions, there exists a subsequence Bn with limiting distribution C such that the limit for n going to infinity of this Bn of t is C of t for any t in which C is continuous. Let me see if I can actually change something here. Let's see what happens if I do this. Why is this not working? Okay. I don't know if this can make some difference. But let's continue. So, okay, we saw Halley's theorem for the limit of distribution functions, and now let's state Kroneker's lemma. Kroneker. So for xn sequence of real numbers with an strictly positive increasing to infinity, and yn, which is the sum of xn over an over ak, and here we have xk. Well, it's doesn't make a lot of difference, I think. If yn converges, then we have that the limit as n goes to infinity of 1 over ak, the sum from k equal 1 to n of xk goes to 0. And now we are ready to finally give the definition. Well, let's put it like this, definition of almost sure convergence. Almost sure convergence. A real valued sequence of random variables xn on a probability space omega h p is said to converge almost surely if the limit for n going to infinity of the realization of this sequence is x of omega for almost every omega in the sample space. So basically the realization, we have a sequence of random variables and we look at the realization of these random variables if these realizations get closer and closer to some value, we say they converge almost surely to that value. And now we have some remarks. Call omega 0 the following event, or the following set, the set of outcomes in the sample space such that the limit inferior of xn of omega is equal to the lim sup. Now, this is simply an alternative formulation of this definition above. Xn converges almost surely to x, almost surely, if and only if omega 0 is such that the probability of omega 0 is 1. And what is the central idea about this? The central idea is that all the events which we consider to be important lead to the conclusion that the limit coincides with, the lim and the lim sup coincide, I think. So the limit, which means basically that the set of outcomes in which this doesn't happen is negligible, which means it has probability 0. Okay, now with this we have an important theorem, which is a characterization of almost sure convergence. And it says that a sequence of random variables xn converges to x almost surely if and only if, for any epsilon greater than 0, the sum over n of the indicators of epsilon applied to this difference is finite, almost surely. So what does it mean? It means that the number of times in which the xn differ from x from a value larger than epsilon is finite. So in the long run, they basically get closer and closer. And let's call this thing here asterisk. Let's go with the proof. Okay, so assume that xn converges to x almost surely. What we have to prove is this thing here, and write y to be this difference, yn, the difference between xn and x in absolute value. This for any outcome in omega 0. From the previous result, well, from the analogous result for real sequences, okay, from the analogous result from real sequences, we have that the sum over n I epsilon applied to yn is finite, yn of omega. For any epsilon greater than 0. And this result was basically the proposition. No, it was not stated as a proposition. Okay, so it was basically this thing here. It was the second remark that we did about the convergence of real sequences. And therefore this holds. Now, so we proved the first implication. Now let this formula here, so this thing here, hold. What we can say or observe is the following. Consider this sequence epsilon k strictly decreasing and converging to 0. And let nk be the sum of the indicators I epsilon applied to this difference. Then we have that the probability of nk being finite, this is 1 for any k, here it should be I epsilon k, question. Shouldn't we have I epsilon k so this probability is 1 for any k because this holds. Now observe that epsilon k plus 1 is less than epsilon k, which means I epsilon k plus 1 is greater than I epsilon k. And this also implies that nk plus 1 is greater than nk. And now consider the events. Consider the events of this form, nk finite. For any k, we have that the sequence of these events nk being finite decreases with k. So the intersection of them is 0. No, is this thing, is the set of outcomes such that the sum over n of I epsilon applied to yn of omega is finite for any epsilon greater than 0. Which in turn is basically omega 0. we have the last line of the proof, which says that hence the probability of omega 0 is 1. Well, it is a quite straightforward claim. It was too direct. We actually have to write some things, some intermediary steps. This thing is the probability, the limit over k of this and k being finite is, and this is by sequential continuity of the probability measure. P is the probability, well, it's the limit of the probabilities. The probability that nk is finite, and this is 1. Because we saw that this is 1. And so for any omega in the sample space, well, actually in omega 0, which is the set, recall, which is the set in which the lim of the sequence is equal to the lim sup, we have that xn of omega converges to x of omega, and this concludes the proof. Let's try to recap what we did. So we saw the definition of almost sure convergence as the situation in which the limit of the realizations is some given random variable. It's the realization of some other random variable. This is a sequence of numbers and it converges to some number, basically. If we saw that the realizations, the sequence of the realizations converges to some number, then we have almost sure convergence. We defined omega 0 as the set in which the limit exists, and the characterization theorem says that xn converges to x almost surely if and only if the number of times in which xn differs from x is finite. And how did we prove this? For the first implication, we simply rewrote the difference and we used the result from real sequences that we have seen. While for the other part, we consider a decreasing sequence of epsilons. We define nk to be the sum, and we want to check, and we know that the probability that this sum is finite is 1. And now this second part, I don't understand it very well. I think we can take a break here. And maybe I will probably practice this again next time. See you.